Yes. Good morning, everybody.
Good morning, sir.
Good morning, Amma. Yes, it's 9 o'clock. Um, See, this is what we have been discussing, the problem solving. So as part of this second part of Unit 1, we had a discussion on all these topics. The problem solving, what problem solving is, production system is, the production rules, and few problems on applying the production rules and the control strategies. That is water jet problem, then the missionaries problem. All these problems we have looked at. This slide which you might have been seeing, this writing of production rules is purely human dependent. That's your perception, okay? And state space set, how do you apply state space first for Mujanir's problem, which would look like a tree which will have always a start state and a goal state, intermediate states, and the arcs. The intermediate states will normally represent the next state, next possible state, and the arc is labeled by the production rule, whatever action that we are going to take, or the operator, you may call it as. All this also we had a discussion, the 8 puzzle problem, the control strategies, the characteristics of control strategies, and then we stepped into this. See, exhaustive searches. See, and as far as exhaustive as the name implies, you'll have a large tree where you completely explore everything. As part of this exhaustive searches, we have breadth first search, depth first, iterative deepening search, and bidirectional search, of which the first two techniques you are quite familiar with, which you might have learned in data structures and might have implemented this in one of the programming languages as per your curriculum. But still, as part of AI also, we should have a discussion. And yesterday we had, not yesterday, in the last class, we had a discussion on the breadth first search and how do we apply breadth first search and how do we generate a tree or a graph using breadth first search. This is what we looked at. See, the process does not change. The process remains the same. Whatever you have learned in data structure, the same process gets applied. So, and this is the way we need to present the algorithm whenever in future, whenever you're asked to present an algorithm, this is the way you need to present the algorithm. Every algorithm should have a name, and below that you should have the input, what input that you're going to provide, and what are the variables that you're going to use within that particular algorithm, and what will be the possible output if the algorithm runs properly. And then you start your method. This is the way of presenting the algorithm. And as in the last class, we have seen it, this particular BFS algorithm, and then we have seen the same problem, that's the water jet problem, the same set of rules that we have used, and followed by the generation of the tree using the BFS water jet problem, BFS for water jet problem. All this was the discussion that took place in the last class, up to last class, not last class, up to last class. And let's move ahead. Indeed, I'm running a bit slow. The second kind of such exhaustive search technique is the depth first search. That also you are quite familiar with. And what does the depth first search do? As one of the girls said in the last class, for BFS we use queues, and for DFS we use stacks. And in the previous algorithm, we are maintaining two kinds of lists. One is an open list, the other one is a closed list. The open list is maintained as a queue, and the closed list is maintained as a stack. Hope you remember this concept for BFS. Now, with respect to DFS, what we do is We'll not go level by level as you did it in the breadth first search. We'll go to the maximum depth possible. See, you start at the initial node, that's the starting node, explore. So on reaching the next level, the first node of the next level, you next explore the its depth. So you go to the deepest level. That's the reason this is called as depth first. Depth first, and there is every chance of reverting back. There is every chance of getting back also once you reach the last node in the depth. So that's the reason we normally apply backtracking over here. So in depth first search, as you may find those statements over here. We go as far down as possible into the search tree or graph before backing up and trying alternatives. This backing up is nothing but the backtracking. Once you reach the lowest level, the deepest level, then what you do? If you get the solution, it's okay. If you do not get the solution, you have to backtrack. That means step backwards and then explore. If that is also not possible, again step backwards and then explore. That's how the procedure runs on. So it works by always generating a descendant of the mostly recently expanded node. Look at this, a descendant of the mostly expanded recent node. Whatever node that you're working on, based on that node only the expansion takes place, and one of the child will be taken into consideration. That child is nothing but the descendant, and then you go to the next level of it until some depth cutoff is reached, and then backtracks. This is what you mean by backing up, coming back. Backtracks to the next most recently expanded node and generates one of its descendants. This is how the procedure normally runs with respect to depth first search. So if you compare this to see in the breadth first search, what is happening? You start at the initial node and expand all the nodes completely at that particular level. That means you visit all the nodes that are present at that particular level. So all those nodes are to be stored in the memory. All those nodes are to be stored in the memory. Whereas in depth first search, only one node is to be stored in the memory. So when compared to the breadth first search, this is memory efficient. This is memory efficient. It requires breadth first search requires more memory, whereas depth first search requires less memory. So we say that DFS is more efficient. In which way? It is with respect to memory. This is memory efficient, as it only stores a single path from the root to leaf node along with the remaining expanded siblings for each node of the path. So this is the thing that you need to take into account. So when compared to the step, this is more memory efficient. And as we seen it in the DFS also requires we maintain two lists in BFS. One is open, the other one is closed. Which data structure is used for maintaining the open list and which data structure is used for maintaining the closed list? I do have 44 students in the class. No one is responding. Am I audible?
Yes, sir. Yes, sir.
Yes, but no one is responding. In BFS, open is maintained as a queue and closed is maintained as a stack. Whereas in DFS, both open and closed are maintained as stacks only. See, open list normally contains the nodes that are to be expanded, and closed list will contain all those that are visited, already expanded. Both are maintained as stacks. That's the key difference between BFS as far as the data structures is concerned. And this is the algorithm. See the representation of the algorithm. As I said, you always give a name for the algorithm. That is the depth first search algorithm. And what's the other things that you need to mention henceforth? The first one is the input. That is the start state and the goal state. These are the two inputs that you're going to provide. What are the variables that you're going to use within this? One is open, the other one is closed, the other one is recording, the other one is successors, the other one. So you can add more or less, that's up to you, based on the convenience, based on the way that you represent the algorithm, you can go with more number of variables also. Okay, and what is the output? What's the possible output? You need to have a path from the start state to goal state. If it is yes, suppose if it is no, simply say no. There is no possibility of reaching the goal state from the start state. As simple. So these three are important. Once you define these three, then go with the actual method. As far as I know, you have been writing this only, step 1, this, step 2, 3. And from here onwards, since you are now third year students, the senior, almost you have the seniority by 2 years. So the things that you need to present, this is the way you have to present with these three statements at the beginning. So the method, initialize the open list. Initialize the open list. So what does the open list contain? The node that you are going to expand. Which node that you are going to expand? The starting node, that's the root node. So you are going to initialize this open list with this, this structure, start and nil. And what does this nil represent is, nil represents the parent of the node. Parent of the node. Does the root have any parent? The root doesn't have any parents. So so its parent is given by null or nil. So you are going to feed the open list with the starting node, that's the root node, along with its parent. So for every node, you should be going with this representation only, because you need to backtrack. So if you want to get back, so what should you know? You should be knowing the parent of the current node. The parent of the current node, you cannot be backtracking. That's the reason we are using this structure. Value that's being stored in the open list or the closed list, you will have in two parts. One part is the node, the other one is the parent. Okay, and initially closed set doesn't have anything, is set to an empty set, null set. The initial state of found is false. Run through the loop. How long would you run through the loop? While there are some nodes available in open, so while open not equals to null set and found is equal to false, keep repeating this. Keep repeating this. Now, remove the first record. What is there that's there in the open list? The root node is there. Remove that. Remove that. And call it as the current record. Call it as the current record. Put this record into the closed list in front of. See, just I hope you are aware of the stack operations and the queue operations. Push this record, say whatever you remove from the open list, call that as the current record, and insert that record into the closed list, that is ASAC. So the record that you have withdrawn, that you have removed from the open list, is now pushed into the closed list. Now check if this the state X is not given over here, you can include state X also. If the state of record X is equal to goal state, that means if this record X is equal to the goal state, then simply say found is equal to true. If you say found is equal to true, here the loop ends, and see here the statement ends, because all this gets into the else part. So again it goes over there. Since found is equal to true, what happens? This condition is false, and this overall condition becomes false. You come over here, you will be displaying your result. Suppose if this state of X is equal to not equals to goal, then what should you do? Then you have to traverse. The else part takes place. So what do you do now? You have to expand. What is that you are going to expand? The current state would be expanded. That's the current record, which is considered as the current state, that will be expanded. So perform expand operation on the state of X, producing, it will have all the branches. It will have all the children, producing a list of records called successors. So whatever list that you are going to see, if I say consider the first node, you will have 3 or 4 children that will be generated. Those 3 or 4 children will be placed in the successors. Okay, create each record by associating parent with its state. This is important. This particular representation is important because we are going to the deepest level, and if you want to get back, definitely you should be aware of the parent of the node, or else there will be no possibility of tracing back when you try implementing this. So what we do is every record that you're going to maintain, the record structure should be the current node along with its parent. Okay, once you place all the nodes that are expanded into the successors, suppose if there are already any records that are available in the closed list are present in the successors, just remove them. So we write it as remove from successors any record that's already in the closed list. Now these successors will be placed open list. See, if I say A is the first node and its children are BCD, suppose if one of these BCD is placed is already available in the closed list, that will be removed, and the remaining nodes will be freshly added to the open list. Now the loop again continues. The loop again continues. This is how the representation takes place. Suppose the discontinuation fails, if found is equal to then true, return the path by tracing the pointers to the parent, because all this path will be available in the closed list. Whatever nodes that are being visited, that's available in the closed list. So you will be retrieving that. Suppose if found is equal to false, you simply say no path is available or you cannot reach the goals. Algorithm clear? You are starting the initial state, which is your root node, and whenever you store that in the list, open list or closed list, you should be storing that as a structure. And the structure of that is the node along with its parent. The node along with its parent. And when the first node that is to be explored is always start node. So the start node is retrieved from the open list and it is explored. Okay, and all those nodes that are explored are placed in the successors, and if any of the nodes that are present in the successors are already available in the closed list, you will be removing them. And the remaining successor nodes will be placed in the open list and the procedure gets satisfied. This is how the algorithm gets applied. Kindly understand the representation of the algorithm. Whatever that you are aware of, the procedure, it's the same procedure, but it with respect to the development of a program for this, from this. That's how the representation has been given out here. So rather than calling this as an algorithm, we can call it as a pseudocode also. It's 80% algorithm statements and 20% pseudocode. Okay. So I'll slightly expand this. This is how, here I'm not going to give you the complete representation, but try understanding this. What is that you are going to have? You have two lists. One is the open list, the other one is the closed list. What's the initial state? We are again considering the waterfall problem only. What is the this is the initial state, 0, 0 initial state. And how will this be represented in the open list? When it is placed in the open list, 0, 0, comma, its parent. What's the parent of the root node? There will be no parent of the node. So this part will be stored in the open list. Now, according to your algorithm, what should you do if the condition is satisfied? That is, the while loop part is satisfied. What is that? What does the while loop say? The while loop says. What does the while loop says? When open is equal to not equals to null set and found is equal to false, then this is going to take place. So based on that, see, this will be now retrieved from the open list and they will be added to the closed list. See, this will be added to the closed list. And now this is your current state. This is the state of, is this equal to goal state? This is not equal to goal state. Since this is not equal to goal state, what happens? You need to expand this. So all the nodes that are expanded will be taken into consideration. See, this is one node that has, see, the complete representation is not given over here. This is one state. This is another state. And you may have further state also. How did you get this state? On applying rule number 2. How did you get this state? On applying rule number 2. So all those states will be placed in this. So what is the current state of this? 5, 3. So see, one of the states is, suppose if I apply rule number 2, If I apply rule number 2, what happens is I get a state which is equal to 0, 0. So that is one state, 0, 0. If I apply rule number 3, I get 5, 3 as the next step. So 0, 0, 5, comma 3. What happens over here? 0, 0, 5, comma 3. 0, 0 is already placed in the closed list. So I'll remove that from the successors list. And what's the other node that's left over? 5, 3 is left over. And what's the parent of 5, 3? 5, 0. So what will be placed in the open list? 5, 3, comma 5, 0. This complete structure will be stored. This complete structure will be stored in the open list. This complete structure will be stored in the open list. And what will be added to the closed list? In the closed list, we already have 0, 0. And this parent, see this one, this is the node that's being expanded. That will be already placed in the closed list. So what is the how? See, whenever you store this record in the one of the lists, open list or closed list, that should be stored in this particular format, the record format 5, 0, 0, 0. Then again, further expand this node. 5, 3. Rule number 2 is being applied. Rule number 2, what does it say? Rule number 2, what does it say? Empty the first jeg. So you will have this state. You will have this state. So this is your current state. This is your current state. This is how you need to generate the session. This is how you need to generate the session. Sorry, what I mean, the tree using BFS. Sorry, BFS. I'll be back in 2 minutes. Okay. Yes, sorry for the interruption. Let's continue with our session. See, this is the way we normally generate the tree or graph using the depth first search. See, these steps are important. You started with this one. What is there in the open list? This is there in the open list. And whenever you store, it is stored as a record structure. The record structure normally will have the current node followed by its parent. And once this is expanded, see, here rule number 2 is applied. When rule number 2 is applied, what's happening? You are getting a state which is 0, 0. That's the reason it has been removed from this successor list. See, whatever node that's already present in the closed list need not be available in the successor list. Once you remove all those nodes, then successor list, say all those nodes, all these are the nodes that have been generated for 50. So this is now expanded and this is now taken into consideration. So this will be your current open list. In the open list, you'll be having currently this node. And what are the nodes that are available in the closed list? All the visited nodes, 0, 0, and nil this one, and then 50, comma 0, 0, the parent of 50. The parent of 50 is 0, 0. That's how the process continues. See, on 5, if you apply rule number 2, what happens? Rule number 2 clearly says, hope you remember these rules. Rule number 2 clearly says that the second jug is to be, the first jug is to be emptied. See this one. Rule number 2. Please recall these rules, these 8 rules. The first rule is filling up the first jug. Second rule is emptying the first jug. Third rule is filling up the second jug. Fourth rule is emptying the second jug. See, we are applying these rules. Based on those rules only, we are generating this. We are generating this. See, on this 03, if I apply rule number, see rule number 1 and rule number 4, what happens? And if I apply rule number 5, what happens? That will be the current state. And why did we place an into mark over here, a cross mark over here? What algorithm, what does it say? Perform this expand operation on the current state, producing a list of records. These we call them as successors. And remove from successor any record that's in the closed list. In the closed list, if any of the record is there, please remove from that. And the many records that are available after removal, those will be added to the open list. This is how the procedure continues. So this is only say here, all the steps are not given. Here, all the steps are not given. So this is a partial generation. At the end, you will have this goal state. See, once you have this goal state, these are all the nodes that are there in the closed list. So what would be your path? Whatever that you have in this will be your path. So you will have a backward pointer from 0, 0 to this 50, 50 to 53. This will be the backward steps if you want to display the result. So you need to understand how we generate this particular tree using DFS. See, in the previous class, in the last class, we have seen how we generate the tree or graph. Okay, a network issue. I've joined. Is my screen visible now? There was a bit of
Yes, sir.
interruption. There was a bit of network interruption. So I'm back. So whatever that's present in this closed list, you need to represent. This will be maintained as a linked list rather than as an array. So if you move from the 0, 0 backwards, all the nodes, not the parents, all the nodes will give you the complete solution path. See, both the things, both BFS, we have obtained the solution, the DFS, we have applied the solution. Without applying any exhaustive searches, also we have got the solution. Now we need to consider which gives us an optimal solution. That's also important. So let's compare the procedures of a DFS and DFS. According BFS has its own advantages, has its own advantages. BFS has its own pitfalls and DFS has its own pitfalls. See, initially I gave you one key difference. If you apply BFS, it is not memory efficient. It occupies too much of memory. Whereas if I consider and DFS, it is more memory efficient. That is one difference you can understand. See, look at the first statement. BFS is effective when the search tree has a low branching factor. That is, if the number of children for a particular node is less, then BFS is effective. If the number of children is more, then this is not effective because it requires too much of memory. It requires too much of memory. And BFS can work even in trees that are infinitely deep because it goes level by level. Doesn't matter how deep the tree is or the graph is. And as I said, see, BFS requires a lot of memory as number of nodes in the level of the tree increases exponentially. And if the goal state is at the higher levels, that is a level number, a less level number, then BFS is a very good method. See, when the BFS is superior, when the goal exists in the upper right portion of a search tree. Upper right portion of a search tree. And BFS always gives an optimal solution. All these are the key. See, both plus and minus have been given over here. This is effective when it has a low branching factor. Low branching factor means it has less number of branches. Less number. You expand any particular node, it will have a limited number of branches. If it has more number of branches, what happens? It requires too much of memory. That's the basic disadvantage of the BFS. And it is not worried about the depth of the tree. It could be of any depth, doesn't matter. It still gives a definite solution. And if the goal solution is to the upper right, that is on that particular line, if it's to the extreme right of that, then this is a very good method. And this always produces an optimal solution. Now taking into DFS, taking DFS, when you consider the DFS is effective, when there are few subtrees, that means you'll be going to the lowest depth, to the deepest level. See, you'll be going to the deepest level. If the number of subtrees are less, then this is effective. Here, when is this effective? When the branching factor is low, this is effective, BFS. Whereas when the subtrees are less, this is effective. Okay, and DFS is best when the goal state, see the difference between this. BFS is superior when the goal exists in the upper right portion, and DFS is best when the goal exists in the lower left portion of the search. That means there is no need to backtrack. There is no need to backtrack. That's the reason it says that DFS is best when goal exists in the lower left portion of the search tree, because After expanding one node, you go to the next level. After expanding that node, you go to the next level. That means extreme left nodes will be taken into consideration. That's the reason they say that DFS is best when goal exists in the lower left portion of the search tree, whereas BFS is superior when the goal exists in the upper right portion of the search tree. Okay, and DFS, this is the negative part of DFS. This can be risky or dangerous when the path closer to the start and farther from the goal state has been chosen. If that means if the path from the starting node to the goal state is too large, then this could be very risky and consumes more time. And the key advantage of DFS is it is memory efficient, because we are not going to store all the nodes that are expanded. Memory efficient as path from the start to current node is stored. And for every node, what is that we are going to store? A record structure will be stored, the current node along with its parent. And another disadvantage of DFS is it might produce an optimal solution, it might not produce an optimal solution. But BFS definitely gives you an optimal solution. So it is up to you which one is to be chosen. So when you have less branching factor, go for BFS. When the number of subtrees are less, go for DFS. When you look into a memory is an efficient factor, then go for DFS, because BFS requires more memory. And when you see at the goal state, it can normally see there's a perception where a goal state normally appears at the lowest level, then go for DFS rather than for BFS. That's how you need to compare both the approaches, the BFS and DFS. See, as of now, in your data structures, you might have studied what BFS is and how you apply it. What BFS is and how do you apply it for a graph. Now, it's not only applying it. We are starting from a goal start state and try obtaining a goal state, reaching a goal state. That's important. And moreover, we are comparing both the approaches and we need to identify which one is better. If you are looking for an optimal solution, always BFS is the best. For an optimal solution, always BFS is the best. So two approaches we have discussed. The third approach is depth first iterative deepening search. This one, depth first iterative deepening search, this is going to consider the advantages of both the approaches. What's the advantage of BFS? If the branching factor is less, this is advantages. When you pick an optimal solution, this is advantages. When is DFS advantages? When there are less number of subtrees, this is advantages. When you look into memory consideration, this is advantages. So what does depth first iterative deepening search is? This is going to combine both the approaches, both the BFS and DFS. So it takes advantage of both BFS and DFS searches on trace. The plus points of BFS and the plus points of DFS are taken into consideration, and using those advantages, this algorithm works. Depth first iterative deepening search. Nodes at a given depth before expanding any nodes at a greater depth. So it expands. So for a particular node, you move from one level to the next. Yes. Any inconvenience? Hello? See, it expands all nodes at given depth before expanding any nodes at greater depth. Expansion takes place. It is guaranteed to find the shortest path. It is guaranteed to find the shortest path or the optimal solution. One, it has to find out the shortest path and memory efficient from start node to goal state. So this is a mixed approach, a combined approach which contains both the BFS and the DFS. So if you are comfortable with BFS and DFS, then we can better understand the depth first iterative deepening search. And this is the algorithm for depth first iterative deepening search. As usual, you will have the first three statements: the start state and the goal state, that's the input, and the local variables that would be used is found, and the output would be whether you have reached the goal state or no. And then the method follows. See, initialize. What is this stands for is, we'll initially start with a depth, lowest depth, that is the first one, where the depth level is 0 or 1. Then as necessary, we keep on increasing the depth level. That's the reason, see, look at this name, depth first iterative. Initially, we start at depth 0, or see in this algorithm, this has been given as depth 1. Next, if there is a need for further deepening, then again we'll increase the depth. Step by step, we keep on increasing the depth as only if necessary. So what we do is, we go with a local variable d, which stands for the depth level. So initial depth level, so you may go start with 0 or 1, doesn't matter, since this is only an algorithm that C language representation or Python representation, where the initial value of this, that's not necessary for us. Okay, initialize d is equal to 1 and the state of found is equal to false. So while found is equal to false, anyhow this is false, repeat this process. Perform a depth first search from the start to depth. Depth first search from start to depth d means, what is the depth d? D is equal to 1. That means you are at the initial state, that is a root node, you go to its next level. That means you consider all the nodes that are present at the next level. Perform a depth first search from the start to the depth. If goal state is obtained, then found is equal to true, our process is done. Suppose if the goal state is not obtained, then we go to the else part. Discard the nodes generated in the sets of depth node. Discard the nodes generated in the set of depth, because the goal state is not found. Discard the nodes generated in the set of depth. Then increase the depth. Are you getting this? I have A here. A has 3 children. So all these nodes will be taken into consideration. Next, I have B over there. B has again 3 children. I'll consider this B, C, these 3 children. I'll not go to C again. See, initially, the depth is not being taken into consideration. Sorry, all the nodes that are present at the same level are not being taken into consideration. See, this has been expanded. I go to this next level. Then only, suppose if the solution is found out here, you will give your answer. Suppose if the solution is not found out here, then only increase the depth. That's the reason this is called as depth first. You always consider the depth. This name, kindly understand this name, depth first. One second. So why is the name given as depth first? Means you always consider the depth first part. And how is the depth being increased is as and necessary, as and if necessary, we are increasing the depth. And at any particular depth, we will not be exploring all the nodes. Suppose if A is the first node, it may have 3 branches. Of this, if I consider the first branch B, this may have any 3. I'll be considering this part. Then I'll not go to C again immediately. I'll increase the depth. That's the reason it is considered as depth first iterative deepening. See, as necessary, I'll not, suppose if there are 10 levels, I'll not go to 10 levels as in DFS. I'll go step by step. I'll keep on increasing the depth step by step. And the increasing step is always 1. The increasing step is always 1. Okay. Consider this. See. Keep an eye on this diagram. This is our initial state. After the first iteration, let's say this node has 2 branches. This one and this one. So next, the second iteration, see what is that I'm taking into consideration? This is being taken into consideration, not this. This is being taken into consideration. Yes, this is being taken into consideration. And this has 2 more. This has two more. I'm going only up to this particular level. If I say, what happens? I consider this, and then I consider this, and then get back to this. See, look at the arrow marks. Did I expand this? I did not expand this at this particular point. If necessary only, I'll go. If necessary, suppose if I'm going to get a solution, if I go to the next step, I'll go that way only. So I'll consider the key features of DFS. I'll consider the key features of DFS, and the initial emphasis will be on the depth. That is the DFS model. So look at this arrow to this, and this, and again. See, look at this. After getting back to this, I go to this, and then I reach back to this. See, look at the next iteration. I increase the level. I increase the level. This is the initial step that you have. See, all this diagram is over here. Now I'll explore this node. I'll get to this. I'll get back to this. Then I'll not consider these nodes, because if it's not going to give a solution, I'll discard them, because it should be memory efficient. Then after getting to this state, I'll get back to this. After getting to this state, I'll get back to this. Are you getting this? I'll try explaining this with the help of an example in the next class. So here the example is not quoted. I'll give you an example for this so that you better understand what best depth first iterative deepening search is. But are you clear with the DFS and BFS?
Yes, sir.
Yeah. So if you are clear with those two concepts, this depth first iterative deepening search is not that difficult. I'll try explaining this concept again with the help of an example if you are not clear. And there is one more technique left over, that is the bidirectional search, as the name very name implies. I'll tell you this, doesn't matter. In the next class, I'll have once again discuss the depth first iterative deepening search, and then finally wind it up with the bidirectional search. So that's all with respect to the exhaustive searches. And then we'll go with the heuristic search techniques. Okay. Okay. Where am I? Amma, please post the attendance. And do not worry, I'll post all this material in Google Classroom as well as Moodle also. So you need not worry about this. I'll also post the notes also for this. But the assignments and the question paper would be totally different. I'm teaching you only the concepts. I'll tell you how you might have seen it already, how the question paper comes. So it will be more problematic rather than the theoretical questions. I'll not ask you what artificial intelligence is, define artificial intelligence or something like that. See, some of the problems I've discussed now. What is a problem? I'll give you a problem and I'll ask you to give a solution for this. The Maisonnet's problem. So you need to focus on these concepts, the second part of first unit. That's how the questions do appear in mid-examinations as well as in the main examination. So your preparation should go that way. So if you do have any doubts, please don't feel shy in asking me, and don't be hesitant in asking me. Openly do ask your questions. Thank you, and you may leave and join the following session. Yes, you may leave the class. I still find students in the class.